Okay, so we're going to talk about 3.6 optimization problems. I just want to remind you that we have a supplement to this. So the problems I'm going to be referring to are on the worksheet, which I've attached to the video. They're not very long problems, but instead of writing all them words up here, I thought that would be better. Okay, so what we're working on is optimization problems. These are classic calculus problems, kind of like related rates are classic calculus problems. I will tell you that once again, these types of problems we've de-emphasized a bit, but they're definitely something we still have to address. So let's go ahead and talk about this. So question one, a manufacturer wants to design an open box. So it's got 5 sides, top is open, with a square base. Okay, so forgive my drawing, but hopefully it gets the point across. We have a square base here. So this is going to be an unknown, so we'll call this x, and then since it's square, this will also be x. And then this is going to be y. With a surface area of 108 square inches, what dimensions will produce a box with a maximum volume? So in optimization problems, you'll either be finding a maximum, like we are in this problem, or we'll be finding a minimum. The way we go about this is very similar, just like when we do maxes and mins in a regular situation. And so the thing here is finding the max or min is just like what we've been doing in class with algebraic problems. What's difficult about optimization problems is we have to come up with the equation that we're going to find the max or min for, okay? And that's really the whole point of this. So let's start with whatever they're asking us to maximize or minimize. So in this case, they're asking for maximum volume. So let's go ahead and take a look at our volume formula. So our volume formula in this case is going to be x squared, because it's going to be the area of the base, so that will be x squared times y. Now the key to any optimization problems, and this is a pretty typical thing, we want to write whatever we're trying to maximize or minimize as one variable. So right now we have 2 variables, so I don't want to use this. I need to write this in one variable. So there's always going to be this second parameter which we have here. So the second parameter we have here is that they tell us the surface area of this open top box is 108 square inches. Okay, so what that means is if we add up all these sides, these 5 sides, we get 108 square inches. So 108 is equal to the area of the base, so that would be x squared. And then we have these rectangles that go all the way around this. So there's 4 of these rectangles that are going to be x times y. So this would be plus 4xy. So that is our surface area, or shows us what our surface area is. And once again, I want to remind you that this is open top. If it was closed top, we would just have 2 times x squared, but this is open top, okay? So now what this allows me to do is this gives me an equation that I can write in terms of one of my variables to plug in here, okay? So in this case, choose whatever one's easier, and clearly what's going to be easier here is y. So I'm going to solve for y. So let's see, I'm going to subtract x squared, and I'm going to divide by 4x. So y is going to equal 108 minus x squared, all divided by 4x. Now what I'm going to do is I'm going to plug that in here. So what I get is, let's call it v of x, because we're writing this in terms of x squared, and then y is this term in terms of x. Okay. Now that from there is really the part that's new. Okay. Once we get this equation, we're going to be finding a maximum or minimum depending on the problem, just like we've been doing in class. So we're talking about critical points, first derivative test, or perhaps testing endpoints. It's going to be one of those methods here. So the first thing we want to do is take the derivative. Now, if we could take the derivative of this, but this would be really quite awful. First of all, it would be awful to take the derivative, because notice you'd have product rule mixed with quotient rule, which would be kind of annoying. But then to solve that would be very, very difficult. So it's going to be important with these problems that we simplify these as much as we can. As I've been talking about in class as we turn out derivatives, I haven't really demanded that you have a simplified version of things. And I still don't really demand that, but just know that if we want to work with these things, we definitely want to make it as simple for ourselves as we can, okay? So what I'm going to do here, first of all, I want to point out that I can take the 108, so I'm going to do this in 2 steps so you can see what's happening here. So I have x squared. I can take the 108 and put it over 4x. And I can take the x squared and put it over 4x. So this is something we've done in the past to make our derivatives simpler, but a lot of you kind of have been skipping that step. Now this is going to be very important. Okay, so I'm basically distributing the division, and then I'm going to distribute the multiplication. So what I'm going to get here is, so I'm going to distribute this. Now the reason why I left it like this is what we're going to see is x squared cancels with one of those x's here. So I'm going to have 108 divided by 4, which is 27, and then x squared divided by x is just going to be x. Okay, and then I'm going to do the same thing over here. So notice x squared over x, that's going to cancel, giving us just an x in the numerator, and then we're streaming this across. So I'm going to have 1 divided by 4, so this would be minus 1/4, okay? And then this is going to be x squared divided by x is x, times x squared, so this is going to be x to the 3rd. Now we have a very, very nice equation that we can find the max or min. So from here, this is going to be very similar to what we've been doing earlier in this chapter. So we start off with critical points. So we want to find the derivative equals 0. Possibly the derivative not existing, but I will tell you in these types of problems that would be a relatively rare thing to happen. Okay. So take the derivative of this. This will be 27. 3 comes down minus 3/4 x squared. I want to find when that's equals 0. Okay. So let's rearrange this. Put 27 over there. So we're going to get 3/4 x squared is equal to 27. Now, I'm going to multiply by 4/3. It's going to be easier to divide by 3 first, so that'll be 9 times 4, that's 36. So I get x squared is equal to 36. So whenever I take the square root of both sides to solve, I do have to consider the negative or positive. So I'm going to have -6 and +6. What I have to realize in this situation, the negative doesn't make any sense. We're not going to have a -6 dimension here, so this will be 6 inches. Okay. Now the last thing I have to do is confirm that this is indeed the maximum value. So one of the things we can do is we can do this like we've done in the past. If there's endpoints, we can plug in all the values. So notice x cannot be 0, right? Because if it's 0, the box doesn't exist. And then at most it could be 108, but it can't be 108 because once again the box wouldn't exist. So there's really no viable endpoint. So what I'm going to do here is I'm going to use one of my other tests. I could actually use the double derivative test or the first derivative test here. I'm just going to go ahead and do the first derivative. So we're looking from 0 to 6 and then to I guess 108. All right. And then all I'm doing is I'm taking values and I'm plugging this in. So I would just choose values that are going to be easy to do. So if I plug 1 into, and I'm just going to plug it into our derivative here, this will be 27 minus 3/4. I don't care about the value here other than it's just positive. And then let's pick another value. And what I'm going to pick here is I'm going to pick 8. And the reason why I'm going to pick 8 is because I can square that. That's 64. 64 divided by 4, that's 16. 16 times 3 is 48. All I care about is 27 minus 48 is negative. Okay, now this tells us everything that we want. Now what I'm going to do is instead of just talking about the derivative going to positive, negative here, I'm going to talk about the fact that it's positive on this entire interval and it's negative on this entire interval. Basically that just rules out the possibility of having another max or min. So we have a max when x equals 6 inches. Okay, so that's our answer. We'll get the y here in a second. They do ask for the dimensions in the problem, so you want to make sure you answer the question. Some people do all the calculus, but then they don't answer the complete question. So that's part of it. Now let's justify that, and that is because v prime is greater than 0 on 0 to 6, and then v prime is less than 0 on 6 to 108. And that ensures that this is indeed the maximum, okay? And then so we get the max of x is 6 inches. To get the y, I'm going to plug in 6 into, where's our y? Right here. So this will be 36, 108 minus 36 divided by 24, and that gives us y is equal to 3 inches. So not my drawing shows y being greater, but that was just my drawing. And that is it. So that is problem 1. Now let's go into problem 2, where we're going to be finding a minimum. But the one thing I want you to understand about optimization, on the front end, it really doesn't matter whether we're finding a minimum or a maximum. The procedure is going to be the same. The big focus here, once again, is this equation. We want to write whatever they're asking for a maximum or minimum, we want to write as a function of one variable. And that will be the trick with most of these. Okay, let's do problem 2. Okay, problem 2. In problem 2, we want to find the points on the graph of y equals 4 minus x squared that are closest to the point 0, 2, which I have drawn here. So essentially what we're talking about is, we were talking about a point on this curve, okay, that is going to be, let's call it x comma y here, okay, and we want to know when that's a minimum, okay. So in other words, another way of phrasing this is, we want to know which point on this curve is closest. We're talking about between these 2 points, which one is a minimum distance, okay. So as I talked about in the last problem, our first focus is to write whatever I'm trying to maximize or minimize as a function of one variable. So our distance here, okay, square root, we're going to use the distance formula. So that is going to be, let's see, x minus 0 squared plus, and then y minus 2 squared. Now, typical thing we're going to have is we have 2 variables here. We've always got to focus on writing as a function of one variable. That's where this equation comes in. We know if it's on this curve that y will be in terms of 4 minus x squared. So essentially I'm just going to replace y with 4 minus x squared. So d is equal to, well, this is just going to be x squared. And this will be plus, and then 4 minus x squared, if I plug that in here, right, so y equals 4 minus x squared, I'm going to have 4 minus 2, so let's call this 2 minus x squared squared. You follow that? So I'm just plugging this in there, and the minus 2, 4 minus 2 will give us 2. All right, now here's the thing. I could proceed from here. So I want to find the minimum distance. So I want to find when this function here is a minimum. So that means I take the derivative of this. If you're starting to think about that, this is actually quite an obnoxious derivative. It's not that hard to take that derivative, but the problem is once I find that derivative, it is going to be very difficult to solve the equation. What I realize is this, and please follow me here. I actually can ignore the radical in this particular case, and let me just explain this to you. Okay, hopefully I can convince you that this is true. We can't always do that. In fact, that would be generally a terrible thing to do. So I'm going to rename this d sub star. It's a different function, but the minimum x value for this will give us a minimum value for that. And here's the reason why. If I think about what a square root does, like, so if I have this y equals square root of x, it gives me a function that looks like this. Now the reason why this is going to work is because square root is always increasing. So the maximum or the minimum input will give us the minimum value. The maximum output will give us the maximum value, because whatever goes in, if it's larger, will give us a larger output. So what that means is if I find the minimum x value here, then plug it into the radical, it will also give us the minimum total distance, because the radical isn't going to change which one's the minimum. This is going to be much, much nicer for us to work with. We're not going to have to do chain rule or anything like that. I could leave it like this and do chain rule, but I would rather simplify it as I talked about in the last problem. So hopefully you understand what I'm saying here. The minimum of this function will get plugged into this, which will give us a minimum of that function. So we're going to focus on this function instead, which is going to be a lot easier for us. Okay, so let's go ahead and distribute this. So this will be plus, so 2 squared is 4. This will give us minus 2x squared, minus 2x squared, so that'll be minus 4x squared, and then plus x to the 4th. Okay, so now I can simplify this. So d sub star, let's call this x to the 4th, minus 3x squared plus 4. Okay, now this is a very easy function to work with. So I'm going to go ahead and start with my analysis on this function. So let's take the derivative of this. This will be 4x to the third minus 6x. That's equals 0. Now the way I'm going to solve this is the zero product property. So let's factor out a 2x, which will leave us with 2x squared minus 6 equals 0. Now let me point out from this, let's move this over here. Okay. From this right here, we get two critical points. One is x equals 0. The other is 2x squared minus 6 equals 0. Okay. Now, we could deal with this. One thing I'll point out to you is that we already sort of see if this is 0, 2, we get this point here. I know what that distance is going to be, but let's go ahead and consider it. And then over here, we're actually going to get two values, right? Because I'm going to get x squared is equal to, let's see, 6, that's 3. Okay, did I do that right? Not what I had before. Oh, I did not. Okay, let's fix that. So if I factor out a 2 here, the problem I had was this is going to give us 3, not 6. Okay. So now put that over there, that's 3/2. So what I'm getting here is I get x equals negative radical 3/2 and positive radical 3/2. All right. Now I have basically 3 critical points. Which one gives us a maximum? Which one gives us a minimum? You know, we're going to go ahead and test these. So basically, I have 2 endpoints. So let me point out, x could be 0. It could be negative radical 3/2. It could be positive radical 3/2. It could also be, x could also be 2, right? Because if it's 2, we'll also get a value. So I'm going to go ahead and compare all those values here. So x, and then once again, finding the max or min for d sub star will be the same as finding the max or min for d. So these are the points I'm going to test. 0, 2, and then let me point out, I'm going to be plugging these into this equation here. Notice I'm going to get the same value for the negative as the positive, which makes sense because it's symmetrical here, right? Because I'm squaring that whether it's negative or positive, that will go away. So the values here for both of these will be the same. So I'll plug those in at the same time. Okay, so if I plug 0 into this, I get 4. Now, if you're saying, wait, that's not the distance, I want to remind you that's d sub star. So to get the actual distance, we take the square root of this value, which we don't really need to do because it doesn't ask us for that. If you plug 2 into this, let's see, we get 16 minus 12. So 16 minus 12, that's 4. So 4 plus 4, that's, wait a second, that should have gave us 2 as well, right? No, okay. So, sorry, because we're talking from there to there. So anyways, if I plug 2 in, that's 16 minus 12, that's 4. 4 plus 4 is 8, okay? And then finally, the radical term. So realize that as I square this, so realize that something to the 4th is I'm squaring that, which would be 3/2, and then I'm squaring it again, okay? Something to the 4th is the same as raising something to the 2nd power and then raising it to the 2nd power again. So square that gets rid of the radical. Square it again, that's going to give us 9/4. Okay, now let's plug it in here. So all that squaring is going to do is get rid of the radical, but it is going to make my negative positive, so this would be minus 3, and then times 3/2, and then plus 4. Okay, so we do want to do a little simplifying here. So we'll call this 9/4. This will be minus, and then this will be 9/2, but let's get a common denominator of 4, so let's call that 18/4, right? So 18/4 is the same as 9/2. And then finally 4, we're going to call that 16/4. So what I get is 9 minus 18, that's negative 9. Negative 9 plus 16 is positive 7, so 7/4. So now these are all our possible candidates. So 0 is 4, 2 is 8. So those are not the minimum. 7/4 is least than all of those. So let's go ahead and over here. Now we have everything we need. They just want the points. So realize that if I take this and plug it into y, so that's going to be this right here, it doesn't matter if I plug in the negative or the positive. Since I'm squaring this is starting to look kind of ugly. So this will be 4 minus 3 halves. So let's call that 8 halves minus 3 halves. So that'll be 5 halves. So our y for both of them is 5 halves. So the minimum distance we have at 2 points, one over here and one over here. So that is negative radical 3 halves, comma 5 halves. That's the one over here. And our other one is the positive radical 3 halves, 5 halves. And those are the points that are minimum distance. Okay, so that's optimization.